Let's go on with the lesson on renewable energy technologies. After having treated the solar plants, we will discuss wind energy, biomass and hydropower. A wind power system consists essentially in a windmill which, thanks to the rotation of its blades, produces electricity. For building applications, the more suitable devices are represented by mini wind turbines, with power up to 20 kW and rotor diameter not wider than 8 meters. Wind turbines can be of two different types, horizontal axis and vertical axis. In the former, which are the most common, the rotation axis is horizontal and therefore the blades rotate in a vertical plane. A typical horizontal axis wind turbine generally has 3 blades, but there are cases of 2-bladed and even single-blade models. A rudder keeps the blades plane always facing the wind direction. A control system slows down or blocks the rotation speed when there is high wind. Vertical axis wind turbines can have different configuration and shape and do not need a system to follow the variable wind direction. For this reason, they are generally very robust and durable, since they are mechanically simpler. Small wind turbines can be installed on a roof, but it is necessary to be very careful about possible vibration transmitted to the building structure bearing them, which may cause fatigue phenomena and noise. In general, for installation on the roof, a few kilowatt vertical axis turbines are recommended due to their low noise level. Because of the shape of the rotor, these turbines have a very limited visual impact. The only downside is the cost, higher than the average. This formula can be used to evaluate the electric power that a horizontal axis wind turbine can produce. P is the electric power delivered. Alpha is a coefficient, depending on the turbine type, ranging from 0.12 to 0.17. D is the diameter of the rotor, and V is the wind speed. As can be noticed, energy production depends on the wind speed distribution, which can be read on the so-called wind duration curve, referred to the number of hours of the year. Biomass consists of organic materials, such as fuel wood, charcoal, agricultural waste, and animal dung, that can be burned directly or processed to produce energy. Nowadays in Africa, biomass is used primarily for cooking, and it must be said that in this sense, the adoption of more efficient cookstoves than those currently widespread is crucial. Using traditional biomass stoves for household cooking requires indeed extensive local fuel collection and is linked to human health and environmental problems. Anyway, biomass can also be exploited by means of more advanced technologies, expanding its use to produce energy for end users of various types, reducing energy waste and GHG emissions and improving the quality of life. Concerning more specifically cooking purposes, it is estimated that the new generation of advanced biomass cookstoves would reduce CO2 emissions and fuel consumption up to 50% and even more. From the simplest to the most innovative, we can mention the followings: the simple Mendeleo stove, the ceramic Gico portable clay stove, the so-called rocket stove, the rocket Lorina stove, and finally, more or less complex fireplace heating systems. Recent research and applications demonstrate that biomass can be effectively used in the field of small cogeneration, biomethane distribution, and second-generation biofuel production. In fact, different technologies are available today, depending on the type of biomass to be processed, the final energy needs to be satisfied, and on the economic conditions. Unlike other renewable sources, to analyze the energy conversion of biomass, it is necessary to consider the complex chain of the overall process in which harvesting and supply have capital importance. Depending on its properties such as moisture content, heating value, and related possible emissions, biomass can be used in many applications for energy conversion, from small stoves to big cogeneration plants. Different treatments can be used to convert biomass into heat and power. Besides the most common combustion, especially for small and medium sizes, pyrolysis and gasification are also applicable. In any case, the scientific community agrees that bioenergy may play an important part in a future low-carbon energy mix. Hydropower produces energy from water sources such as the ocean, rivers and waterfalls. Small-scale hydropower is one of the most cost-effective and reliable energy technologies that can be used for generation of clean electricity. Hydraulic power can be captured wherever a flow of water falls from a higher level to a lower level. The generator is typically represented by a turbine, which works thanks to the rotation of its blades. The vertical fall of the water is known as the head, while the volume of water passing per second is called flow rate. It is generally better to have more head than more flow, since this keeps the equipment smaller. The general formula for any hydro system's power output is this, where P is the mechanical power produced at the turbine shaft. Eta is the hydraulic efficiency of the turbine. Rho is the density of water. G is the gravity acceleration. Q is the volume flow rate passing through the turbine, and H is the effective pressure head of water across the turbine. The best turbines can have hydraulic efficiency ranging from 80 to over 90%, although this will reduce with size. Microhydro systems, smaller than 100 kW, tend to be 60 to 80% efficient. The annual energy output of a hydropower plant can be estimated using the capacity factor CF, as shown in the next formula, where P is the power output as defined before, and CF is the capacity factor, which is the ratio of the actual output over a period of time to the maximum potential output in the same period and depends on the boundary conditions such as water availability, maintenance needs, equipment failures, and so on. Typically, it is higher than 50%. There are various types of turbines, which can be categorized mainly into impulse turbines and reaction turbines. This chart can be used to guide design choices. Each type of turbine works best within defined operating regions in terms of head and flow rate. So, today we have shown how energy can be produced also by exploiting wind, water and organic materials at affordable cost and reducing environmental impacts.